So I asked what would happen if we compounded interest an infinite number of times per year. Well, that actually gives us a brand new formula, and this is actually the best possible compounding for an APR. This is the one that will give you the most return on your money. It's called continuous compounding, and we switch formulas here. So the word continuous means we need to use this formula. And the formula is A is equal to P, which is the principal, times E, and E is a number that's already programmed into your calculator. E is approximately 2.71828. And if your calculator doesn't have that E option, then you can just type in 2.71828. So P times E raised to the APR, the interest rate, times Y. And we also have to pay attention to the order of operations. The variables are the same. A is your future value. P is your present value or your principal. APR, interest rate given as a decimal. Y is the number of years you leave it in that account, and it doesn't necessarily have to be an integer. If we left it in for 6 months, Y would be written as 0.5. But again, if your calculator doesn't have the value of E already programmed in, then you type it in as 2.71828. So try this problem. $10,000 is invested in an account earning 5% interest. Find the amount in the account after 5 years if interest is compounded continuously. So use that formula. So using the order of operations, I would determine the value of 0.05 times 5. That's in the exponential position of this E, that's my base. So I would find that value, I would raise E to that power, then I would multiply that result by 10,000. This would give me $12,840.25. Now compare that to what we did earlier. We had the same amount of time, 5%, but it was compounded 365 times a year. That result was $12,840.03. So notice when we go from 365 times a year to an infinite number of times per year, we only gain about 22 cents. But if I were given a choice, I would always choose continuously because I know in most cases, maybe not every single case, in most cases, continuously would provide me the bigger return. All right, so let's talk about something called effective yield. This is something that a bank must disclose when they're offering a savings account at a particular percentage rate. They should disclose their annual percentage yield. And it's the actual percentage by which your balance increases in 1 year. It's also sometimes called the effective yield. Now, if you are calculating your interest one time a year, annually, then the APR that's stated is the APY, your annual percentage yield. So if it's done once a year, you earn the same that was advertised. However, if you compound that interest more than once a year, your annual percentage yield is actually larger than the quoted annual percentage rate. So, hey, if I'm earning more, I'd like to know. So, compounding more than once a year, the annual percentage yield is actually larger than the annual percentage rate. And again, the bank should list both APR and APY. But the APY is actually what your money really earns. So we look at what happens to an investment in just 1 year. Look at its increase over 1 year, and it's the relative increase. Ooh, we're using something from the last chapter. Relative increase. That's like our relative difference and relative change. Same thing, same formula. We look at it over a 1 year period. So this is just the same thing as what's the new value minus the old value divided by the old value. So you find out the difference in the two and divide by your old value, which is basically your principal. You start with $100. At the end of the year, you have $120. Subtract them and divide by the principal, $100, and that'll tell you your relative increase, which is also your APY. So try it for this example. Find the APY. $1,000 invested, 1 year. The account earns 3.5%. At the end of that year, your account has $1,036.73. Calculate the annual percentage yield. It's not a difficult calculation. The new value is the $1,036.73 minus the old value, which is your investment, the $1,000, divided by the old value, which is your investment of $1,000. So it's the 36.73 divided by 1,000, which is 0.03673. And if we multiply that by 100 to get a percent, like we did before, the annual percentage yield is 3.673. So even though the advertised APR was 3.5%, you actually earned 3.673%. So hey, not too bad. Annual percentage yield. So let's work on wrapping this up. I have a quote from Albert Einstein, and he actually referred to compound interest as the greatest force on earth. Pretty strong words from one of the smartest men to ever live. If you'd like to read more about him, you can go to this website that I have right there. Anyway, interesting reading. So here's bottom line, working with section 4B. Answer these questions. Which do you think is better, simple interest or compound interest? If you had your choice, I hope you would choose compound interest. You earn more money. When might each of those be used? Remember, we saw simple interest and made a statement that simple interest is maybe when you're working with bonds, or actually maybe treasury bills, savings bonds. Compound interest when you're dealing with banks and savings accounts. Okay, which would you prefer? Interest compounded monthly or interest compounded quarterly? Which one would give you the better result? Based on what we've done, I hope you said quarterly. More times it's compounded, the more your money will earn, or the more money you will earn. Which would be better? Interest compounded daily or continuously? I'd go with continuously. The more times it's compounded, the better return you'll get. So what's APY? It's the actual percentage by which an investment grows in 1 year, and it has to be a 1-year period only. You look at the interest earned in 1 year. What type of growth does an investment earning compound interest follow? Remember, we looked at those graphs, simple interest, compound interest. Compound interest was exponential growth. And one last true or false question. APR is always less than APY. This would be false, because APR, whoops, I can't write that down. Remember, we said APY was equal to APR when interest is compounded once a year, but we said APY was going to be greater than APR when interest was compounded more than once per year. Oh, shoot, APY is greater than. Whoops. It's greater than APR when interest is compounded more than once a year. If it's once a year, the two are equal. Okay, so let's do this last wrap up. Okay, suppose you put money in an investment that has an interest rate of 3%, it's compounded monthly, and you leave it there for the next 18 years. Here's a little bit of a twist. How much would you have to deposit now so that in the next 18 years you would realize $100,000, or the amount in the account would be $100,000? It's a little bit, we'll have to do a little backwards work, but think about it for a minute and think about the formula. Can you determine which one is the missing variable? Did they give me a value for Y? Let's see, number of years, check. I've got 18 for Y. Did they give me a value of N, which means how many times a year I'm going to compound it? Yep, I've got a value of N. It's 12. Did they give me a value of APR, the annual percentage rate? Yep, I got a percentage rate of 3%. So the question is, does the $100,000 represent the A, the amount in the account after 18 years, or does it represent the P, the amount you're investing? After reading this, we realize that the $100,000 is the money you want in the account after 18 years. That $100,000 is A, that future value. So what we see here is a little bit of an awkwardness because the variable that we're wanting to find out a value for is P, the principal. How much would I have to invest to get $100,000 in 18 years? Okay, sprinkle in your numbers and then try to devise a plan to solve this for P. You'll have to use some algebra. So on the right, I've plugged in the values of A, APR, N, and Y, the number of years. I'm trying to solve for P, so let's actually do some simplification on the right. Let's find out the value of the 1 plus 0.03 over 12, and let's find the value of that exponent, 12 times 18, that's N, the number of times per year it's compounded, times Y, the number of years. Let's find that base raised to that power and then see where we can go from there. So if you take 1 plus 0.03 to the 12th power, find that 103 divided, oh Lord, I'm getting tongue-tied. If we take 1 plus 0.03 divided by 12, find that number and raise it to the value of whatever 12 times 18 is, you should get 1.714850874. Remember, we don't round any of these problems till the very end. Well, actually, I hope you see this. This is just a simple algebraic equation to solve. P, the principal, times this number we just got can be easily solved for P if we just divide both sides by the 1.714850874. If I divide both sides by that value, I can solve for the principal that would have to be invested to get $100,000 in 18 years. So divide that out. So to answer the question, how much would I have to deposit now to get $100,000 in 18 years, I would have to deposit $58,314.11 now to get $100,000 out of that account in 18 years. Little algebra, but not very difficult. More practice with that formula. Let's wrap it up with this last scenario, and what we see is a graph. And let me make that just a little bit smaller so we can see it all in one screen here. So here's what this graph represents. The horizontal scale represents a year. It starts from 1964, increases 2 years, 1966, 68, all the way to 2012. So we're looking at time on this X horizontal axis. On the vertical axis, we're looking at the typical interest rate that a bank offered. And so we can see there was a median. If I looked at all these bank rates throughout these years, and I found the median or the average of those values, the average of all those values is 5.6%. And this is a monthly average for a 3-month CD, certificate of deposit. So think about maybe, depending on your age, here in the 60s, 1964, 1968, 1970, describe from the graph what kind of interest rates people were earning in the bank. I see in 64 they were earning about 4%, 1970 about 8%, 1974 the banks were offering like 12% interest, 1980 between 80 and 82, so somewhere around 81, bank accounts were earning almost 19% interest. Pretty crazy, but look what happens. 1986, it's down to 6%. 1990, maybe 1992, it looks like it's at 6% again. Looking at the trend of interest rates offered, the banks offered your investment over the years, what we notice is a terrible decline. Look at 2004, you were getting 2% interest on your bank account investment. It rose a little bit, but look at 2010 and 2012. It is hovering right above the 0 mark. Actually, right now, you're lucky to get 0.01% interest. You might get 2%, 3%, not 2% or 3%. This is 0.01%, or you might get 0.02%. The percentage that you can earn on your money right now in a bank account is very, very small. What kind of impact does that have on people who put money away for retirement and are now having to live off of that, but they're only getting this amount of interest? Okay, think about it. I was putting money in the bank in the let's say in the 70s, and now I'm wanting to retire, or let's see, 70, wanting to do some retiring, but my money's only earning a very small percentage rate. Maybe earlier I could live off of the interest. Maybe I could live off of the $30,000 of interest I was making on my investment. Now, instead of making $30,000 on my investment, might be making $3,000 or $300 on my investment. What a dramatic decline in income that I was planning for my retirement. Just terrible interest rates right now. So you can see what type of effect that would have on those who retired and hope to live off the interest for the rest of their lives. At this point in time, you see people getting second jobs after their getting another job after their retirement because of this type of situation. Well, I hope you've learned something for Section 4B. And please let me know if you have any questions, and go on to the homework in my math lab for Section 4B.